Hi friends, welcome to this channel. So in this video, we are going to look at problem 2964, number of divisible triplet sums. This is a newly appeared problem, and in this video, we are going to address this problem using a strategy similar to sum. Actually, we are going to work with the remainder. In other words, we want to use the modulo operation in mathematics. So first, we are going to quickly digest the requirement, and then we look at the coding. And in between, if necessary, we can give a walkthrough. So here, we are given a zero-indexed integer array called nums, and an integer d. So we want to return the number of triplets, the I, J, K, such that they are different, and that the sum of these three numbers is an integer multiple of this given d. So here we have three examples. In example 1, the output is 3. So in the explanation, it lists all the possibilities. And in the second example, so this is very special, right? Because all the numbers are unique, right? All the numbers are 3. So similarly, example 3 is a continuation of example 2, but with a different d. Right? In this case, the remainder is 0, because no matter which 3 numbers you choose, the sum will be none. But none modulo 6, you are going to get 3, right? Never been 0. So this output is 0. And the constraints are the following. So I'm going to focus on this first one and the last one. The length is bounded above by 1000. So this is actually not a very large number. But if you do it using a cubic time complexity solution, then you are going to have 10 to the power 9. But it's quite possible that you cannot pass all the test cases. The last one is basically a consistency assumption. Basically, we assume that d is greater than or equal to 1. So in other words, we exclude the possibility that d being 0, right? So with that said, we are ready to look at code. So this problem, it had some hints. So these hints are actually very suggestive. Basically, follow the hint, you should be able to write a very straightforward solution. But here, what I'm going to do is to work with remainder. But there are mainly 2 steps in our algorithm. The first step is that for each pair ij, so we want to associate with the remainder. So their sum or modulo d. So here I write capital A to represent this nums list. So once we get this information, for example, if you use example 1, you can get something like this. So if you see sum the first 2 numbers, so you get 6. 6 modulo 5 is 1. So that's why we associate this k. So this is one of the pairs that have 1 as remainder. Then you can see 0 and 4, right? 0 and 4, that's you get 11. 11 modulo 5 is also 1. So this is another one. So in this example, there are 4 pairs, right, associated with the remainder 1. So here, the length is 5, right? So 5, if you choose 2, that you are going to get 10. So there are 10 pairs. You can see here is 4. Associated with 2, there are 3. Associated with 0, there are another 3. So in total, we have 10 pairs. So this is the one step. So then step 2 basically is a 2-sum problem. So we are going to do a linear scan to find how many valid triplets ending at the third index key, right? So I'm not going to walk through here for now. So now let's first look at the coding part. The coding will be rather straightforward. Basically, we just need to implement the first one. That is, we get some information, and then we implement essentially 2-sum, but we need to use some filter. So now let's look at the code. First, I'm going to get this length of the nums. This is just for convenience, right? So now I'm going to call this map here aux. So it's going to be a dictionary. So here I'm going to use default dict. I'm going to use list, or you can use set, because all the element tuple in the values, this must be unique, right? So then we can do a double for loop. So for I in range, so because I is the first one and j will be one larger than n, so we want to start. We want this right here n minus 1. So the index will be ending at the n minus 2, right? Then for j, so we want it to be strictly larger than I. So we start from I plus 1 inclusive. And then when ending at n minus 1, right? And then we can see the key we are going to do is nums I plus nums j. Then take remainder. So and then we want to aux. So for this key, we don't need to check if this key is inside this dictionary, because we are using this default dictionary. If the key is not in the dictionary at the very beginning, so this will give us a empty list, right? So then we just need to append this ig. So put it as a tuple. You can make it a list equally well. So this is the first step. Let me step 1, right? Get the information and to run a toSum, right? Problem or variance, right? So now let's look at the second one. So step 2, linear scan. So essentially we have practiced quite a lot of such problems, and we have some videos on. So using the technique, we term it as dict and check, right? Or sometimes use set and check, right? So here essentially we do toSum, but we with filtering, right? So now let's first initialize a result variable. So this is a counting variable to count how many triplets are valid, and then we do so linear scan for k in range. So let me first write this like this, because we know actually k should be at least 2, right? If you have 0 or 1, you have no room for ig, so we can start from 2, right? But if you start from 0, it will work because we have filtered out in the counting. So then the current number, so it will be nums k modulo d, right? So notice that we can always write it like this, modulo d, because d is greater than or equal to 1. In other words, it's not 0. So now what we want to see, because here for the number nums k, so it has a remainder current modulo d. So what we want to see in order to have an integer multiple is d minus the current. But we want to take another consideration. If this current is 0, so this will be d. But d is a multiple, so we are going to take an additional modulation. So in other words, if the current is 0, here d, so d modulo d will give 0. In other words, if we see an integer multiple, then we want to see a pair corresponding to multiple of these. In other words, 0 in the key, like here, right? So now we have this, and then what we want to do. So we are going to get first aux get this required key, right? Otherwise, if not, just use empty list. So among those, so there are some are valid, some are not valid, because you can imagine this will be some list of tuples ig. So we want g is strictly less than k, right? So we can increment the result. We can use a iterator comprehension. So 1 for the ig in this one. So if this g is strictly less than k, right? So this will do the counting. That's what we mean that this is the filtering, right? So in other words, if we do not consider this one, it's nothing but the toSum. Now we can do the return. We return the result. So this forms a valid solution format to this problem. So now let's do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the cases. So now let me come back to the first example, right? Let's give a quick overview of this code. So here we have this list, right? So the D is 5. So we can associate with ij the remainder. So this is the step 1, what this step 1 does. So here, for example, you have 0, 1, it has sum equals 6, modulo 5 is 1, so we have 0, 1. So 0, 4, so we have 3 plus 8, 11, so has a remainder 1. So 1, 4, so 1, 4 is the same as 3, 8, right? So 2, 3. So 2, 3, so we have, this is 2, this 3, so 11. 11 modulo 5, you have 1, right? So if you look at, so 0, 2, so 0, you have 3 plus 4, that is 7. Remainder is 2. So 1, 2, the same, right? And 2, 4, 2 and 4. So 4 plus 8 is 12. 12 modulo 5 is 2. So it's associated with this remainder. And then you have 0, 3. So 0 and 3. You have 10. 10 is a multiple of 5. So it's associated with 0. Similarly, 1, 3. So you have 10. And 3, 4. Let's see. 3 and 4, you have 15, right? It's a multiple. So if you have D equals 5, at most you have 5 keys, right? Running from 0 up to and include D minus 1, that is 4. So this is step 1. So now let's do the counting. So we do a linear scan to find how many valid triplets ending at the third index key. So here I count key equals 0, right? And the key equals 1. Actually, we don't need to consider this 2 because we need key greater than or equal to 2. But if counting it will help understand the logic. So for example, if k equals 0, we get a naught is 3. 3 has a remainder over 5 is 3. So we want to pair with ij having remainder 2. So this will be the pairs. But the k is 0, it's too small, so it's no valid ones. So now let's ignore 1 and look at 2. When k equals 2, we get a2 equals 4. So we want to pair ij has remainder 1. So those 4 are the valid ones. But notice that our key is 2 now. So we cannot include 0, 4, 1, 4, and 2, 3. So we can only have 0, 1. In other words, 0, 1, 2 is a valid one. So the triplet will be 0, 1, 2, right? So here we have 0, 1, 2. So now let's look at k equals 3. So when k equals 3, so the number is 7. So the remainder is 2 or with respect to 5. So we want to pair with pairs having remainder 3, but we don't have those pairs. So we continue. So when k equals 4, so a4 is 8. So modulo 5 is 3. So we need to pair with remainder 2, right? So those are the 3 valid ones. But our key now is 4. We cannot include 2, 4. So we have 0, 2 and 1, 2. In other words, the triplets is see 0, 2, and 4, and 1, 2, and 4. Notice that the elements at 0 and 1 are the same. So right. So we have this 2, right? So this is where the 3 comes, right? So I guess with this walkthrough, you should have a better understanding about the logic. So now if you look at the code, again, it should be a breeze or rather simple, right? So with that said, I guess that's it for this video. Thank you.